Hello, we are from Zhejiang University. Here we will introduce our research on vehicle motion planning for crash mitigation in unavoidable collision scenarios. The outline of my talk is as follows. First, I will introduce the background and related work of our research. Nowadays, motion planning in dynamic scenes, especially when sharing the driving space with other traffic users in urban areas, has become far more challenging than that in near-static driving scenes. However, in extreme situations without enough space or time to stop, even if the ego vehicle is fully autonomous, no matter what invasive measures are taken, the collision accident cannot be effectively avoided. Most motion planning algorithms focus on how to avoid accidents in potentially emergency scenarios, while very few have contributed to how to reduce the crash injury in the unavoidable collision via motion planning. Sometimes a failed attempt to avoid a collision by AEB, AES, or both does not lead to the least crash injury. Therefore, we are motivated to find a new algorithm that can mitigate the crash severity into minimum level when the crash will be unavoidable. Existing algorithms that considers crash severity level can be mainly divided into two categories: the crash avoidance algorithm and the crash mitigation algorithm. Crash avoidance algorithm that takes crash severity level into consideration have its advantage in minimizing the loss of the generated path, but it does not consider the unavoidable crash. Crash mitigation algorithm that includes the unavoidable crash into its structure improves the planning performance in different scenarios. But the crash severity index estimation model only considers the kinematics change of an accident and ignores the forces. Secondly, I will introduce the algorithm structure of our research. The structure of our proposed algorithms contains several parts. Reachable trajectories of ego vehicle are sampled. With the motion prediction of other vehicles, the possible crash is detected. If the collision is unavoidable, the crash severity indexes of each sampled trajectories is calculated, and the trajectory with the lowest CSI is selected as the optimal trajectory for crash mitigation. Thirdly, I will give a brief introduction of our planning by considering crash severity. To find the optimal trajectory, the crash severity index CSI is chosen as the objective, which is related to the state changes of both interacting vehicles. It can model oblique collisions and is more generalized than commonly used delta V model. The principal direction of force PDOF reflects the collision patterns and thus is the pivot for the calculation of CSI. To determine the PDOF, the equations on the right should be solved, which are related to the momentum change of a collision. Because of the nonlinear equations, the iterative optimization method would have huge running costs. To meet real-time demands, an accelerated computing method via neural network is introduced to solve the nonlinear equations. The equations can be rewritten in the form of 5 inputs and 1 output, K0, namely tangent PDOF. Therefore, the neural network structure is designed as shown in the right picture. After the network is constructed, the CSI can be calculated real-time, and the optimal trajectory with comparatively low risk of collision is chosen. Here we use the closed yield curve to sample the trajectories. For computation efficiency, 41 trajectories are chosen for each given acceleration, with the interval of 1 degree of initial front wheel steering angle. To track the optimal trajectory, the Model Predictive Control (MPC) is adopted to minimize the lateral position error and yaw angle error. To validate the proposed algorithm, we carried out a simulation in MATLAB Simulink. An occluded intersection is chosen as the simulation scenario. The ego vehicle is close to the intersection center, while the objective vehicle is approaching at an extremely high speed. The collision is unavoidable, and the CSIs of different avoidance strategies are compared. The left two figures present the closed-based trajectory samples for steering only and braking steering combined strategies, and the corresponding crash severity evaluation results are shown in the right figure. If only AES is adopted, an optimal selection of trajectory is steering to the left, which leads to an oblique rear-end collision with a minimum CSI of 0.16. If only AEB is activated, there will still be a side impact collision, but the estimated CSI is lowered to 0.151. This indicates AES-only strategy may work well in avoiding a collision, but is risky in mitigating the crash severity for an unavoidable collision. If using combined braking and steering, the crash severity index can be further lowered to 0.142, meaning that integrated AES and AEB function can greatly reduce the collision injury. Because there is a certain error in predicting the state and property of the other vehicle, the sensitivity analysis of the influence factor of the error is carried out. Different prediction of the mass ratio of the vehicle body stiffness. 不算，再来一次。Because there is a certain error in predicting the state and property of the other vehicle, the sensitivity analysis of the influence factor of the error is carried out. Different prediction of the mass ratio or the vehicle body stiffness will change the amplitude of the CSI curve, but the shape of the curves does not change significantly, and the shape of the curves partially deforms as the vehicle speed changes. This is because that the change in speed will cause the point of impact to shift. However, the final decision-making point doesn't change much. As a result, even if we made a prediction not that precise, it will not much influence the final decision-making results. We also deployed a real car experiment to test the real-time performance of the algorithm and the trackability of the trajectories generated. The same occluded intersection scenario is chosen as in the simulation. For sake of safety, the obstacle vehicle only occurs in virtual world. The ego vehicle first accelerates to the target speed. When the unavoidable collision is detected, the CSIs of all sampled trajectories are calculated, and the optimal trajectory with least crash severity is chosen. Then the vehicle tracks the optimal trajectory via MPC and begins to decelerate and steer. The tracking errors are shown in the figure. Finally, I will make a brief conclusion. The main contributions of our research are as follows. First, we propose an algorithm to handle the crash mitigation in the case of unavoidable collision, which includes a generalized crash severity index model suitable for various collision patterns. Second, simulations show that by considering crash severity, our planning algorithm can achieve better crash mitigation performances than current collision avoidance-oriented algorithms. Finally, real vehicle experiment and sensitivity analysis demonstrate the proposed algorithm can be deployed real-time and provide reliable and safe performances under conditions with model uncertainties. Therefore, our proposed crash mitigation algorithms can be promisingly applied in emergency driving scenarios. This work is supported by Department of Science and Technology of Zhejiang. Thank you for watching. Let's work together towards zero fatality vision.